Article 250.6 of the National Electrical Code addresses the prevention of objectionable current over grounding conductors or the grounding path. This requirement dictates that the grounding of electrical systems, circuit conductors, surge arresters, and conductive non-current carrying materials and equipment must be installed and arranged in a manner that avoids unwanted current flow. The purpose of this is to ensure that the grounding system functions effectively as a low-impedance path for fault currents and to mitigate issues caused by stray currents. Objectionable current, in this context, refers to current flowing on grounding conductors that isn't due to an electrical fault. Such currents can arise from various sources, including unbalanced loads, ground loops, or interactions with nearby electrical systems. These currents can lead to several problems, including nuisance tripping of ground fault circuit interrupters, or GFCIs, inaccurate readings from sensitive electronic equipment, and even corrosion of metallic components. To prevent objectionable current, several strategies can be employed. Firstly, proper bonding of all metallic components of the electrical system is crucial. This ensures that all conductive parts are at the same potential, minimizing the possibility of current flow between them. Secondly, careful consideration should be given to the routing of grounding conductors. Avoid creating ground loops, which can occur when grounding conductors are connected in multiple locations, creating a circular path for current to flow. Thirdly, isolation techniques can be used to isolate sensitive equipment from the effects of stray currents. This may involve using isolation transformers or optical isolators. Article 250.5 bone, on the other hand, pertains to the use of grounding electrodes and their connection to the grounding electrode conductor. This section requires that a grounding electrode, such as a ground rod, ground plate, or underground metallic water pipe, be connected to the grounding conductor system via a dedicated grounding electrode conductor. The grounding electrode conductor serves as the primary path for fault current to return to the source in the event of a ground fault. It must be sized appropriately to handle the available fault current and must be securely connected to both the grounding electrode and the grounding conductor system. The purpose of this requirement is to ensure that the grounding system is effectively connected to earth, providing a low impedance path for fault current to flow back to the source. This helps to quickly clear faults and minimize the risk of electric shock. A critical aspect of Article 250.5 bone is the requirement for a dedicated grounding electrode conductor. This means that the grounding electrode conductor must be used solely for the purpose of connecting the grounding electrode to the grounding conductor system and cannot be used for any other purpose. This is to ensure that the grounding electrode conductor is always available to carry fault current and is not compromised by other electrical loads. Now, addressing the potential conflict between these two articles, it's important to understand that they serve different but complementary purposes. Article 250.6 focuses on preventing objectionable current from flowing on the grounding conductors under normal operating conditions. Article 250.5 bone focuses on ensuring that the grounding system is properly connected to earth and can effectively carry fault current during a fault condition. These two requirements are not in conflict because they address different aspects of grounding system design and operation. In fact, they work together to ensure the overall safety and effectiveness of the grounding system. By preventing objectionable current, Article 250.6 helps to maintain the integrity of the grounding system and prevent nuisance tripping and other problems. By ensuring a dedicated grounding electrode conductor, Article 250.5 bone ensures that the grounding system can effectively clear faults and protect against electric shock. To further illustrate how these two articles work together, consider a scenario where an electrical system is installed in a building with a metallic water pipe. According to Article 250.5 bone, the metallic water pipe must be used as a grounding electrode and connected to the grounding conductor system via a dedicated grounding electrode conductor. Now, suppose that there is an unbalanced load in the electrical system, causing current to flow on the grounding conductors. According to Article 250.6a, the grounding system must be installed and arranged in a manner that prevents this objectionable current from flowing over the grounding conductors. This may involve using proper bonding techniques, avoiding ground loops, and isolating sensitive equipment. By following these requirements, the electrical system can be grounded effectively and safely, minimizing the risk of electric shock and other electrical hazards. In summary, Article 250.6 and 250.5 bone are not in conflict. They are two distinct but complementary requirements that work together to ensure the proper operation of the grounding system. Article 250.6 prevents objectionable current, while Article 250.5 bone ensures a dedicated grounding electrode conductor. By understanding these requirements and following them carefully, electrical professionals can design and install grounding systems that are both safe and effective. The NEC, or National Electrical Code, is a comprehensive set of standards for electrical wiring and equipment in the United States. It is developed and published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC is widely adopted by state and local jurisdictions, and it serves as the primary reference for electrical safety in the country. The purpose of the NEC is to protect people and property from electrical hazards. It covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is not a law itself, but it is often adopted into law by state and local governments. This means that compliance with the NEC is mandatory in many jurisdictions. The NEC is organized into chapters, articles, and sections. Chapters cover broad topics, such as wiring methods or equipment. Articles delve into specific aspects of these topics, such as grounding or overcurrent protection. Sections provide detailed requirements for specific situations. Understanding the structure of the NEC is essential for navigating the code and finding the information you need. Grounding is a critical aspect of electrical safety. It provides a low impedance path for fault current to return to the source, helping to quickly clear faults and minimize the risk of electric shock. Grounding also helps to stabilize voltage and reduce electrical noise. The NEC contains extensive requirements for grounding, covering everything from grounding electrodes to grounding conductors to equipment grounding. Proper grounding is essential for the safe and reliable operation of electrical systems. Overcurrent protection is another important aspect of electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. This helps to protect wiring and equipment from damage caused by overloads and short circuits. The NEC contains detailed requirements for overcurrent protection, including the selection, installation, and sizing of overcurrent protection devices. Wiring methods refer to the types of wiring and cabling that are used to connect electrical equipment. The NEC recognizes a variety of wiring methods, each with its own advantages and disadvantages. Some common wiring methods include rigid metal conduit, electrical metallic tubing, flexible metal conduit, and non-metallic sheath cable. The NEC specifies the allowable uses for each wiring method, as well as the requirements for installation and support. Equipment installation is another important area covered by the NEC. The NEC contains requirements for the installation of a wide range of electrical equipment, including lighting fixtures, receptacles, switches, and appliances. These requirements are designed to ensure that equipment is installed safely and in accordance with manufacturer's instructions. The NEC also covers special occupancies such as hazardous locations, healthcare facilities, and swimming pools. These occupancies require special electrical installations due to the increased risk of electrical hazards. The NEC provides additional requirements for these occupancies to ensure the safety of people and property. In addition to the NEC, there are other codes and standards that may apply to electrical installations. These include state and local building codes, as well as standards from organizations such as Underwriters Laboratories, or ALL, and the Institute of Electrical and Electronics Engineers, or IEE. It is important to be aware of all applicable codes and standards when designing and installing electrical systems. Keeping up with the latest changes to the NEC is essential for electrical professionals. The NEC is updated every 3 years, and each new edition includes changes and revisions to the code. These changes may be based on new technologies, industry best practices, or lessons learned from electrical incidents. Electrical professionals should make sure they have access to the latest edition of the NEC and that they are familiar with the changes. Training and education are also essential for electrical professionals. Electrical work is complex and requires a thorough understanding of electrical theory, wiring methods, and safety practices. Electrical professionals should participate in ongoing training and education to stay up to date on the latest technologies and techniques. Licensing and certification are often required for electrical professionals. Many states and local jurisdictions require electricians to be licensed or certified. Licensing and certification demonstrate that an electrician has met certain minimum qualifications and has the knowledge and skills necessary to perform electrical work safely and competently. Electrical safety is everyone's responsibility. Electrical hazards can be dangerous and even deadly. By following the requirements of the NEC and other applicable codes and standards, electrical professionals can help to ensure the safety of people and property. Homeowners and other individuals can also take steps to improve electrical safety in their homes and workplaces. This includes having electrical systems inspected regularly, using qualified electricians for electrical work, and following basic electrical safety practices. Now, let's delve deeper into the practical applications of Articles 250.6 and 250.5 bone. Imagine a scenario in a commercial building where sensitive electronic equipment, such as computer servers, are used. These devices are highly susceptible to electrical noise and interference. If objectionable current is present on the grounding conductors, it can introduce noise into the system, potentially disrupting the operation of these devices and causing data loss or equipment malfunction. In this case, Article 250.6 would be particularly relevant. The electrical system would need to be carefully designed and installed to minimize the possibility of objectionable current. This might involve using isolated grounding systems, which are designed to prevent ground loops and minimize the flow of current on grounding conductors. It might also involve using shielded cables and connectors to reduce electrical noise. In addition, regular testing and maintenance of the grounding system would be essential to ensure that it is functioning properly and that objectionable current is not present. On the other hand, consider a manufacturing facility with heavy machinery. These machines often draw large amounts of current and can generate significant fault currents in the event of a ground fault. In this case, Article 250.5 bone would be of paramount importance. The grounding electrode system would need to be robust and properly connected to ensure that fault current can quickly and safely return to the source. This might involve using multiple grounding electrodes, such as ground rods or ground plates, and connecting them to the grounding conductor system with appropriately sized grounding electrode conductors. Regular inspections of the grounding electrode system would be necessary to ensure that it is in good condition and that the connections are secure. Furthermore, the size of the grounding electrode conductor is crucial. The NEC provides tables and guidelines for determining the appropriate size of the grounding electrode conductor based on the size of the service entrance conductors. Using an undersized grounding electrode conductor can compromise the effectiveness of the grounding system and increase the risk of electrical hazards. Bonding is another critical aspect of grounding. Bonding refers to the connection of all metallic parts of the electrical system to create a common ground path. This includes metallic conduits, enclosures, and equipment frames. Proper bonding helps to minimize voltage differences between different parts of the electrical system and reduces the risk of electric shock. The NEC contains detailed requirements for bonding, including the types of bonding conductors that are allowed and the methods for making bonding connections. Surge protection is also an important consideration in electrical system design. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes or other events. SPD are typically installed at the service entrance and at sensitive equipment locations. The NEC contains requirements for the installation and connection of SPD. Ground fault circuit interrupters, or GFCIs, are another important safety device. GFCIs are designed to detect ground faults and interrupt the flow of current before a person can be injured. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. The NEC contains requirements for the installation and testing of GFCIs. Regular testing of GFCIs is essential to ensure that they are functioning properly. This can be done using a GFCI tester, which simulates a ground fault and verifies that the GFCI trips. Electrical inspections are an important part of ensuring electrical safety. Electrical inspections are typically performed by qualified electrical inspectors who are trained to identify electrical hazards and ensure compliance with the NEC and other applicable codes. Electrical inspections are often required before a new electrical system is energized or when significant electrical work is performed. Working with electricity can be dangerous, and it is important to take precautions to avoid electrical hazards. Always energize circuits before working on them and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. If you are not qualified to perform electrical work, it is best to hire a licensed electrician. Electrical safety is a shared responsibility, and it is important for everyone to be aware of the risks and to take steps to protect themselves and others. Firstly, ensure all electrical work is performed by qualified and licensed electricians who are familiar with the NEC and local codes. Secondly, regularly inspect electrical systems for any signs of damage or wear, such as frayed wires, cracked outlets, or loose connections. Thirdly, use surge protectors to protect sensitive electronic equipment from voltage spikes. Fourthly, install and maintain GFCIs in areas where there is a risk of electric shock, such as bathrooms and kitchens. Fifthly, avoid overloading electrical circuits, which can cause overheating and fires. Sixthly, keep electrical cords and appliances away from water. Seventhly, never attempt to repair electrical equipment unless you are qualified to do so. Eighthly, teach children about electrical safety and keep them away from electrical hazards. Ninthly, if you experience any electrical problems such as flickering lights or burning smells, contact a qualified electrician immediately. Tenthly, have your electrical system inspected regularly by a qualified electrical inspector. The grounding system's effectiveness is also influenced by the soil conditions surrounding the grounding electrode. Soil resistivity, which is a measure of how well the soil conducts electricity, can vary significantly depending on factors such as moisture content, temperature, and the presence of salts or minerals. High soil resistivity can impede the flow of fault current to ground, reducing the effectiveness of the grounding system. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to treat the soil with conductive materials to improve its conductivity. Regular testing of soil resistivity can help to identify potential problems with the grounding system. Lightning protection systems are designed to protect buildings and other structures from lightning strikes. These systems typically consist of air terminals, which are mounted in the roof of the building, and grounding conductors, which connect the air terminals to the grounding electrode system. The grounding electrode system for a lightning protection system must be separate from the grounding electrode system for the electrical system. The NEC contains requirements for the installation and grounding of lightning protection systems. Electrical drawings and diagrams are essential for understanding the design and operation of electrical systems. Electrical drawings typically show the layout of electrical equipment, wiring, and circuits. Electrical diagrams, such as single-line diagrams and schematic diagrams, provide a more detailed representation of the electrical system. These drawings and diagrams are used by electricians, engineers, and other professionals to install, maintain, and troubleshoot electrical systems. Troubleshooting electrical problems requires a systematic approach. The first step is to gather information about the problem, such as when it occurs, what symptoms are present, and what equipment is affected. The next step is to use test equipment, such as voltmeters, ammeters, and ohmmeters, to measure voltage, current, and resistance in the circuit. The results of these measurements can help to identify the source of the problem. Once the source of the problem has been identified, it can be repaired or replaced. NEC also addresses the use of flexible cords and cables. Flexible cords and cables are used to connect portable appliances and equipment to electrical outlets. The NEC specifies the types of flexible cords and cables that are allowed for different applications, as well as the requirements for their installation and use. Flexible cords and cables should be inspected regularly for any signs of damage or wear. Damaged cords and cables should be replaced immediately to prevent electrical hazards. The NEC also covers the use of electrical boxes. Electrical boxes are used to enclose electrical connections and to protect wiring from damage. The NEC specifies the types of electrical boxes that are allowed for different applications, as well as the requirements for their installation and support. Electrical boxes must be properly grounded to ensure electrical safety. The NEC also addresses the use of conduits. Conduits are used to protect wiring from damage and to provide a raceway for pulling wires through. The NEC specifies the types of conduits that are allowed for different applications, as well as the requirements for their installation and support. Conduits must be properly supported to prevent them from sagging or bending. The NEC also covers the use of cable trays. Cable trays are used to support and route cables in commercial and industrial applications. The NEC specifies the types of cable trays that are allowed for different applications, as well as the requirements for their installation and support. Cable trays must be properly grounded to ensure electrical safety.